have approximately 1.5 hours, maybe 1 hour for talk and maybe some presentation of the software. I can see that we have 42 participants, partly from our department, partly our students, hopefully some students from different departments from the Czech Technical University, from Faculty of Mechanical Engineering. So I would like to welcome again Dr. Kegler, and please, floor is yours.
Dear Dr. Vavra, thank you very much for this kind introduction. Welcome to all the students and listeners in Prague from Graz. As just mentioned, I'm working in AVL. I'm a mechanical engineer, studied or finished the study end of the 80s, and had made several things in AVL and in diagnostic area first, and since end or beginning of this millennium, I can say I'm dealing with design of experiments and calibration technology. So I'm happy that I can share some of the thoughts with you now, and I've made a slide presentation. The question is, do you see already something? No, most probably not. There must be somewhere a sharing button, right? Is it working now? Do you see something coming?
We can see only you.
Only me. That's not what I fully intended, but maybe it will come. Share. The question is now, which of the screens?
Yes, perfect.
Now it's visible. Yeah.
This one where now my mouse is. What is at the end? Not what I want to show you yet. No, it is not. There should be a title slide. Design of experiment. Do you see this?
Yes.
Yes.
So I'll hide this presenter view, which I don't like, to be honest. And do you see also my mouse? There are still two screens. This is the presenter mode you should see.
Yes, we can see also the mouse.
Thank you very much. So sorry for all that inconvenience for the first 10 minutes. I do not intend to talk 1.5 hours. In contrary, I'm not sure how a discussion works here, but if anybody has a question somewhere in between, you're very welcome to put it. And I'll try to reserve anyway some time for discussions at the end. And well, the title is, I'm not sure if you've heard about, if you're aware about, if you're expert in, all might be possible. Design of experiments is a technique, well known, not new. But the application as powerful method for powertrain calibration is not so public known. And we have developed a tool in AVL called CAMEO supporting this task. And I would like to start with a certain overview about the development, small history about the last 13 years and the challenges in powertrain calibration and its evolution through over this period. So if we look back in 1995, engine control unit, and if we talk about calibration, we talk about filling data like curves, maps, or also single values into a control unit, which is a part, for example, from engine as decisive component of a drivetrain. And in 1995, such a ECU had about 500 labels, so single values, curves, or maps. A curve is dependent on one variation parameter, a map dependent on two variation parameters, like ignition timing, for example. Well, this was a task taking 2 years to fill this data already at that time, tested in the all eventualities, but still it has place in the head of one person And depending, it was also a clear assignment that this engine should go in this passenger car and maybe 2 types, but not more. Or if it's a light duty, heavy duty, or off-road machinery. Legislation was associated quite clear. And yeah, it was challenging already at that time, but it changed. 10 years later, we had about 10 times the numbers of labels, so 5,000 variables to be filled. The functionality was already that complex that it's typically needed 2 persons to understand all that, what's going on in an ECU. Variations of the vehicle was at least 6 or more. Passenger car, for example, where the engine went in. Very often, automated gearbox was already applied. And if we look to the truck, also the range was already up to full load, where a clean calibration was requested by legislation. And yes, as only changing the parameters is comparable fast, also development cycle time reduced. So it was more complex, more persons, more teamwork, shorter time. If we go to now and a little bit in the future, and this again, we have to handle more labels. Again, number more than 50,000 in ECU alone. But the gearbox, meanwhile, typically is not only automatic switching and have several modes, it's also storing energy and delivering electric drive back. So a P2 hybrid is more or less state of the art, what you should develop now if you want to meet the CO2 requirements and the emission legislation. It's also helpful to have it. And the variants, just with the same hardware of drivetrain, different hardware in the vehicle and different data set, they are typically far beyond 50. Also 200 is not seldom. And in legislation, it's again sharper. We have now real driving emission. That means it's not so clear in which kind the driver will move through this map when he's operating the car. So to sum this up, it's well known, the challenge. We have the CO2 targets. It's an increased complex system. Engine after treatment systems are needed. Also, OBD is a big topic. Hybridization is more or less state of the art. And also the cost of testing, just the testing, is more when you have to cover real drive conditions. In addition, you have to consider it during development to fulfill all these partly conflicting targets. Further, the update cycles are again shorter, and the vehicle portfolio is wider. More people have to work together. Also, teamwork is partly worldwide distributed in the industry. So a lot of challenges. And yeah, again, multivariant application. If we look to RDE, and this is especially the challenge from RDE, temperature range is the starting condition from 0 to 30. It will be extended to -7 to 35. The cycle itself is not NADC anymore. It is something up to 160 kilometers per hour. Just a third is city, a third rural, and the rest is highway. It takes not 20 minutes, but 120 minutes maybe for one test. And yeah, also the altitude will come. And the car, by the way, is not empty, it's loaded. Heating is switched on, air condition on. So it's really challenging. And there's one important element of the solution in this development tool set. And this is what I want to talk about today a bit. It's CAMEO. We have now the version 4.3. And it can be connected to more or less any development environment. I will explain soon what I mean with development environment. It's, for example, an engine testbed. And the idea is to make comparable few measurements in an intelligent test automation with the target to get models, behavior models, also this graph we will see later, for the responses of the engine, depending on the set of calibration data. So whether you maybe change the main timing, the rail pressure, the boost pressure, the EGR rate. Is there a question? If yes, you're very welcome. If just background noise, please just mute. But please be encouraged just to put any question always. Well, the idea is to get such behavior models, and then you can comparably fast request an optimizer to search for you the right setting for your targets. And sometimes you have conflicting targets, like here you see this, there is a Pareto front where two targets, so there's no lower value for that, whatever it is here, if you want to reach a minimum, maybe fuel consumption and NOx, except you go increase the other value. This is a Pareto front in 2 dimensions. So a Pareto front is always 1 dimension lower than the number of targets. So it's a curve in this case if you have 2 targets. It would be a surface if you have 3 targets. Well, too much detail for now. It works in many development environments. So an engine testbed is one where you have a system under test, the engine plus control unit. But you could have also the whole vehicle system under test on a chassis dyno or on a powertrain testbed, or even much earlier in the process. And not only, this environment is going also in parallel still after start of production. It's a so-called virtual testbed, where only the ECU itself is real. Even the engine is modeled with an real-time capable but semi-physical engine model capable to respond in terms of altitude and pressure, so pressure, humidity, temperature. So it's an important tool which is more or less here in parallel to the process. And all of that environments, always you have the question, when I change several parameters, in which direction should I go to get the desired best optimum? So there are now, for example, for the real driving calibration, typically 4 steps supported by CAMEO. The first one is you have a number of real driving cycles just as they occurs. And for sure, you're interested to get somehow worst case cycle. But if you plot this as function of speed and torque, you see here maybe green, maybe blue dots, can be several. They're spanning up a range. And with your measurements on a test bed, you would like to identify the engine behavior in all the range in terms of operating conditions, speed and torque. And in addition to that, you want to calibrate maybe 8 influencing parameters like rail pressure, start of injection, boost pressure, and so on and so forth. First injection, second injection, always timing and quantity. Or on a gasoline engine, valve timing, again, also EGR rate. Lambda you don't touch. Maybe you have injection timing also, if it's a direct injection engine. So you have always 1 or 2 handful calibration parameters to balance for your optimum. And these are then changed in addition. Sorry. These are changed in addition. And then there is a technique used, we will talk about today a bit more, design of experiments. And that means we plan a comparable low number of points in order to get a trend, a model. And if you look, for example, to a smoke model, which is typically ugly to model, highly nonlinear response of an engine, Then you can imagine, typically it's not that tight like sketched here for one parameter, that there are several possibilities to go through these points, more flat or more cornery. And the active TOE is then, while the test is running, automatically building the model and asking, for example, at that point, if there is a target where it should be below, it's 2 FSN or even lower, you try to estimate this value if it's really 2 here, and maybe it comes back lower, and puts additional points here, so to get a high model quality in the area when this maybe 8-10 dimensional space, somewhere the corner is going up. And this is important because when you decide for calibration, you should be with a certain robustness inside a certain range as constraint. So active TOE is supporting to put the measurements in the right place. Then also here it's not necessary to have automatic modeling. This is a big benefit for calibration engineers, because we worked with several universities, very much with the TU in Vienna, to improve this automatic modeling and the modeling itself. And in former times, it was even a specialist work. You need to understand which terms to put in, which type of neural network to select, doing something with the weighting functions. And now we have automatic modeling, which gives you a good solution right away. If you're expert, you still are allowed to overrule this, but it's not easy to get better modeling like we have here. And last but not least, if you have now the models, if you can move all around in the map, you can request cycle optimization. So that means that this worst case cycle of real driving, you put in all the grid points of the maps constraints to be inside your target you want to deliver as OEM in terms of emission and also fuel consumption, to ensure that later on in the field, and the legislation is now that far that out of the field after 100,000 kilometers, a car will be picked out, put on a test stand and checked, and there must not be a certain factor increase of the emission. And so the OEM has to consider also that engine after treatment systems get a bit poorer over lifetime. And so to get this done properly, you have to consider all the range, all the parameters, and there is really helpful to have then such models and to populate the maps. And this is then the calibration for that emissions, for example, emission and base calibration for delivering power and the values as expected. So I mentioned now several times design of experiments, and now it becomes a bit more academic. So TOE, what is that? If you would be here in person, I would like to ask this question around. Who has heard about? What is it? Do we see somewhere hands or something like that? I know it from my... you could move your hand if you want, right? Or just tell something if you want. So it's, I assume now it's not known so much. And so I have some sentences to describe it. It's an abbreviation standing for design of experiments. So according to statistical rules, you plan where in this multidimensional space you should put your measurements to be able to make response models. And yes, these measurements distributed should be a low number, and it should be fitting for what you expect in terms of non-linearity of the model. It can be simpler if you say it's just a pure linear model or a polynomial one up to third order, not more non-linearity. If you say you have somewhere corners in or even hills up and down, you need to measure more. Well, and the target is to get statistically assured empirical models to predict in the whole design space the results, what might come out in fuel consumption, in emission, in noise, whatever you model. This is the target, and this is how one could describe. If I would ask you, how old is DOE? Since when does it exist? Who would try to make a guess? Just from the lifetime of the founder, which, or the first person who really wrote down these ideas, was Sir Ronald Fisher, and the ANOVA table is still in the DOE evaluation. Yes, he died already 62 of last century, and it's about 100-year-old. So in 1924, DOE started, and he developed it for agricultural questions. So we are already unhappy if we have to measure 5 minutes to get a stable measurement on an engine test bed. But to get a response on an agricultural question, you have to wait at least a year until you can quantify the harvest as function of fertilization, dung, soil, and so on. And this was his task. He made simple models, linear only. And further in history, the nonlinear stuff, this came more or less in the 80s. The engine application started in the 90s of last century, still based on polynomial models first. And since the early 2000s, we have neural networks. Nowadays, one calls this same technique artificial intelligence. So it's, yeah, the cooking recipe is still related, I would say. And why not just try all combinations? This is the very first approach. And if you have not many parameters, you can do this also. So if you have only one parameter and you want to get a trend, you have 5 measurements in the area where we expect that this parameter influence your result. Yeah, you make 5 measurements. That's easy. It can be done manually. If you have 2 parameters, well, again, 5 steps in each direction. If it's efficient, you have 25. It's already something. If you have 3 parameters, it's getting hard. 125 measurements to get the influence of the responses. And if you have 4, you see it's already a bit slower, 625. And the point is just this is an exponential trend, always only 5 steps. So still limited nonlinearity. And if you would make a task like RDE calibration in this manner, the engine would not stand the measurements. It would be for sure somehow defect before you end the measurements. So it's not an option. It does not simply not work anymore. And nevertheless, I go back in this case to a bit kind of an e-motor question. If you have 1 parameters like the ID, IQ, there are 2 components of the current amplitude an inverter can set. And if you are sitting in front of a eDrive test bed and you would, let's say, manually measure some results, and you are able to measure the motor efficiency or even the total efficiency with inverter, you might get such a slightly noisy result. And if you see such a result, as we are engineers, we typically do in our brain quite automatically something like that. We fit the trend inside. We smooth this small noise, which is hard measurable. Efficiency to measure is not a simple thing. And we make a kind of smooth trend. Well, and this is where DOE starts with turning around the question. In first time, it says, what do you expect, which kind of shape? Is it a second order model, maybe? This would be a second order polynomial model. I write soon the formula. And yeah, if you have this model, you could trust the model and take this position as best one, despite this point might be a bit lower than those one. The trend shows that this is the right one, and you can differ effect from measurement noise. You took maybe 10 measurements in this case. If you would apply DOE and you say you expect a second order model that this efficiency curve follows a quadratic coefficient, a linear coefficient, and a constant, so a second order model, then if you ask DOE, the absolute minimum to identify such a trend would be 3 measurements, but it's not statistically assured. It's not enough. DOE would add at least 2 points to double check whether this assumption is correct. And then this is maybe astonishing the first time, it would spend also repetition points. So at least on 1 point, measure several times, also to get an information how good is your experiment repeatable. In terms of controlling the device, the same like in terms of measurement accuracy. Altogether, repeatability of the experiment. In some, you're already in this example, maybe faster, but this is not the important thing, at least not for 1 dimension. This distribution is now made that you can fit very good second order model, and you further get an estimation whether second order model fits, and you can do the same. You can say, this is my best point, I get the best efficiency here. And in addition, you get something else. You get a so-called confidence interval, which takes also the reproducibility of the repetition point in account, and therefore also a trustability to the model itself. So this confidence interval can be made for, maybe you have heard about, for statistical measurements without any influence. There we talk also about a confidence interval. Typically, it's selected 95% confidence. And in this case, it's more or less the analog thing where you just have a model and you say with 95% probability, the true model is somewhere in this range. And I would like to visualize a bit what it means. You could get exactly the same model like this one with a more or less noisy measurement. And if you look on the confidence interval of that noisy measurement, it might look like that. What do you think does this mean? And this would mean that with 95% probability, the model looks like that or like that. So at the end, you can judge either you improve your measurement quality or you forget the influence of that parameter. You might be better off because this seems just noisy. You can't interpret it with statistics significant trend. And this is another very important topic of model order reduction to, in such a case, in best case, take a linear, but not a quadratic term into the equation. If we look to the 2D example, let's say this is the truth which we know already up front, just to better understand. And you have there 2 parameters. It's in this case a gasoline engine, the start of injection, and here is the ignition angle. And this might be the stability of combustion. And if you go through in one direction, so keeping the spark advance constant and change the start of injection, then you might see, okay, here I will have my best stability. Okay, to be careful, I double check also in the other direction. So you don't make full factorial, you don't have the time. But you feel you should do it somehow with intuitive approach. And say, okay, quite good. In this direction, it's getting even better. So I'll go here at that point. And as I'm careful engineer, I double check if the other direction is still the same. Oh, now it has changed. I'm here. Here's even better. And then you double check again and again. And after a certain time, you have found your desired most stable point. In this case, and it's maybe also assured in the next direction, and you are here. In this case, you spend 20 to 30 measurements. If you would take DOE, in this case, I took again the electric example, and you say, and at the end, this curve shape behind is a second order model. In 2 dimensions, it would have 2 quadratic parameters, 2 linear. This is the so-called interaction term. This is what we see here. It is dependent on the one parameter where the optimum is in the other direction, and for sure a constant. So 6 parameters. So at least again for the mathematical minimum would be 6 points at least. 1 you need for the interaction. Domain parameters, 3 steps for each parabolic trend. Then DOE would add other points to be sure to have a good, that the assumption is somehow correct, and some repetition points. So typically, classically designed for a second order model, the so-called central composite design would take 13 measurements for 2 dimensions. It's already comparable less, and this is at the end the target of DOE. And I just mentioned interaction, and this may be also an important topic, therefore, as an extra visualization. If you have here on the z-axis any system response, and here's a variation factor 1, maybe to give an example, the system response could be the pleasure to eat and to taste a good meal. And the variation factor 1 is maybe the quantity of meat, and the variation factor 2 is maybe the quantity of beer. And you could, yeah, it's a bad thing for interaction, because if it would be beer, you would best have both. That's correct. Let's say the second parameter is the quantity of pudding. And if you would assume that it's also going up if you mix more meat into the pudding, you might be wrong. So this would be without interaction, but if you then measure and try this, you get a strong interaction. So either the one or the other, but both together, this doesn't work. So this would be an example for interaction. Also very important to be covered and typically missed if you make the approach just as seen before with this 1 factor at a time, which takes then more effort at the end. So now to have a fast, very basic comparison of options when you want to investigate something. You can make a so-called dragnet or full factorial investigation. The advantage is you will have covered the whole design space. For sure, you can also build a model. You will get an almost exact fit, high quality. Disadvantage, if you have no repetition point, and this is typically missed out in full factorial investigations, you do not even realize a drift. So if you run here through in the meander and it's getting warm while the measurements and you don't consider that, you get a temperature trend in this direction. And then the most difficulty, if you have more than 3 parameters, it's typically just not possible anymore. Too expensive, too much effort. As human beings, we typically tend to make then 1 factor at a time. We want to see the trend in the one direction, in the other direction. The benefit, if we have few measurements, that's true. The disadvantage, we miss completely interaction. For example, we might see, in this direction it's best, in this direction also best here. I'm done, I've found my best optimum. You never have been here, you didn't see it even. So you miss out completely interaction effects. Further, again, no drift sensitivity. Modeling, if you want to make a model has no information here, doesn't know what to do here. So confidence interval will go up in this range. And for that, design of experiments is the right alternative. It has an advantage to have a complete design space with only a few measurement points, similar low number than here. And yes, you can model, you get the statistical information about model quality, you cover the interactions. One disadvantage is you have to learn the method once, and typically you have to get trust into application of the method. I had an example from a fuel cell guy from the university, and he had heard about DOE and tried it by himself, made a second order model for a fuel cell polarization curve, which is a bit nonlinear, not too much, but a bit. And he said, this is rubbish, doesn't work. Yes, didn't work. So before that, he had 250 measurements done for 2 dimensions to identify the polarization curve, so the current and the temperature are the input parameters, and the decrease of the voltage of the cell is the output parameter. And when applying DOE with the classically second order central composite design, he came out, I think, with the 13 measurements and was not content with the result of modeling. And that's right. We applied then together a de-optimal design with 48 points, and it was nearly exactly the same what he has got with the 250 points before. So this is what classical DOE can do. And now how to apply it if you want to use it for calibration. If it's not engine, I've heard, for example, in steering, very often the word tuning. You can also use the same just to do a hardware optimization in simulation, as long as the parameters can be varied. This sketch, more or less, is valid for everything of that. Typically, we have one system or unit under test, and this has mechanical parts like an engine and the control unit like an engine control unit. And then you have somehow an environment where you simulate the load, for example, for the engine on an engine test bed. This is a dyno. It can be extended with a vehicle simulation, with altitude simulation, as far as you want. What we have always is that we can operate now this engine under different load conditions at the one hand, and also on different control unit settings. And this need not be only a combustion engine, it can be also an electric component of your drivetrain, for example, inverter and e-motor. Always you will have some input parameters, and you are interested in behavior models, and you want to reach a certain behavior to be calibrated for your mechatronic unit. And the classical approach, very often if you sit as person, as human in front of a test bed, is that you make some settings, observe the measurement devices, and make a one factor at a time approach, one parameter at a time. And this is at the end the trial and error method. You get then again a result, like we had these single buttons coming, the 10 times if you have only one parameter. And this method is very intuitive, very widely used, but has some drawbacks. First, the quality depends on where you start, and also on the experience and on the time the person is allowed to spend. Typically, it's not traceable. If you have a similar task 1 month later, it's also not easy to be reused. Maybe you remember something, but you have to do it again and again, typically. So what we suggest, or what can be done if you connect Cameo to such an environment, is that you start with a task planning. You start up front, what I want to do. I want to reach lower noise emission, for example, and nevertheless consider the efficiency targets, maybe increase it even a bit, or typically they've done a lot in simulation up front, but temperature conditions, you're not so sure upfront what you can reach. Further, also, you have to validate whether the temperature models are really reached in the hardware. So at the end, it's similar. Also here, you have several number of parameters. It's the operating condition, defining the power. Then there's only, for the efficiency, one main parameter. It's this ID-IQ ratio. You can change the voltage of the DC supply. You can change the cooling flow of the, if it's a cooled rotor also, but mainly on the inverter side. You can change the frequency of switching and also the environment temperatures. And you see here already how it looks if you apply then DOE. It is typically from a safe point starting, and we see a bit of that strategy later. So you try to put the system under these conditions, and then you measure the results, and with these results you can get your output models. With the output models you can ask an optimizer. And if you have such models and you are then the user, you can just put what you want to reach. Maybe two conflicting targets. Maximize the torque and keep the temperature low. And at the other hand, you get then suggestions back, for example, such a Pareto front where you can decide where you want to go, maybe on that corner, high torque, not too hot, and get the settings for your inverter calibration or configuration. Well, this is now an example what was really reached in a practical customer exercise. So the customer had a full factorial approach, exactly those parameters. And it took him, despite he had one parameter, some parameters only two levels, so only linear, and had a lot of work to ensure that nothing is violated or getting too hot, destroying the inverter. It took him 511 measurements, and it was for sure possible to model. It was excellent model quality. A second, we applied this classical DOE approach, which already with adaptive DOE, I don't go into detail now, is a certain first development what we had in Cameo, and is effective. So we could get similar results with 45 measurements only in the whole range. Model quality was not that excellent, but it was still good. And last but not least, we applied our latest state-of-the-art, what we call active DOE. So it has a de-optimal start design and then goes into the area where of the interest. Maybe you can see here even there are more points in the area where the Pareto front is and less outside. These blue small things are measurement points. So in this case, we took 57, got the same excellent quality, and at the end, the customer was quite happy with this result. So what is now Cameo, what it's standing for, how it is packaging design of experiments for the calibration engineer first. So it's our target to take out a bit of that complexity, which is growing at the end with the great options we have with mechatronic units. We just need to change a bit of the software, and the whole behavior of the mechatronic unit changes. And we want to deliver a complete solution for powertrain testing and optimization. And the main features are automation, highly automated testing, intelligent testing. We support this model-based calibration solution, so design of experiments to identify this behavior model and then use the models for calibration. And despite its more or less structured workflow, it's still highly customizable and compatible to many systems. And maybe the name Cameo might also be interesting. So the name is already more than 20 years old. I joined the group in 1998. There it was quite young, and it was an abbreviation for computer-aided method for engine optimization. So this is where we are coming from. But meanwhile, it turned out that not only the engine has such challenges, also other drivetrain components already in the simulation, and therefore we would like to be understood as computer-aided method for every optimization. Yeah, it's if it's not face-to-face, it doesn't come like that, but it's for sure a kind of joke. Let's say one shouldn't overinterpret the name. Name is just Cameo. And yes, how to optimize something? That's not a question. First, we have to understand how whatever is the unit under test, is behaving. What are the options? First, we should have a development environment, whether it's now an engine test bed, a pure simulation, or maybe a Cruise M model, or even a fire simulation, very slow, detailed simulation, 3D fluid dynamics of a fuel cell, for example. We need to find out how it behaves. What can we do? We can put the parameters in all possible combinations. So we had already this picture in mind. So it's not a good idea. It's exploding exponentially. Second, we could be experts, or even not, might guess somehow the best combination that might fit. It's also not a technical approach and no industrial approach. So we should make use of the options and possibilities. Design of experiments is delivering. This is, by the way, a bit a sketch of how this determinant is maximized, is a coefficient determinant. And behind that maximization, so to give a best leverage for the single polynomial coefficients of a defined polynomial equation, this is behind this de-optimal design. Yes, this is for classically polynomial modeling, the most effective design, which we really recommend as long as you can use polynomial models. Well, the next is then how to apply these parameters to the unit under test. One could make a list, print it out, give it to the testbed driver, sit at a testbed, type the numbers in, observe the limits. It's a kind of boring job and also risky that you might miss some limits. So it's not what we recommend. We recommend to make an automated test run. And this is also supported, and this is a key to support this, and it's not so easy, as we will see soon. But it's state of the art since more than 20 years. We really can, let's say, manage that. If the test is done, the second big step is to analyze the data. First, are there outliers in? Is the data usable? You could read big tables or help with some 2D diagrams, all a bit difficult. We suggest some graphs and finally make a model out of it. This is, by the way, again, a fuel cell with the polarization curve. This is the typical curve. And it's depending also on some other boundary conditions. In this case, 4 in addition, so 5 parameters. This is perfect. U is perfect to identify such behavior. Well, and then at the end, if we have such models, what we can do with it? We can choose the best parameters, but first the question, for what? We need to make up our minds what we do best before we start the test and define what we want to reach. Well, the language of the optimizers and mathematicians is also not the ones of the mechanical engineers. we would like to have it in human language. We would say we want to get a maximum in this direction, but please don't exceed the temperature, the NOx, the soot, whatever we limit. And this we can tell an optimizer, and he comes then back with suggestions or a clear optimum. If you have only one target function and an unlimited number of constraints, this will lead to a clear optimum. If we have more than one target function, so target is like a spring pulling towards one direction, minimum fuel consumption, minimum NOx, minimum soot, it's a conflict. It's not one point. There are several options. You can reduce fuel consumption, but you will get disadvantage in the other ranges. So define what is the optimum, then make use of the built models. And yeah, you could use it also, the models by hand, and do a similar thing like one factor at a time, and you will see automatically interactions, and it's already much faster. But you could do it manual and sweep through the intersection plots, giving you understanding of the system under test. So I would not strike through it that hard, but it's not that fast and helpful than asking an optimizer who will come back with a suggestion, and then still you can go through the intersection plot, move along Pareto fronts, and so on. We will see it later. And if you have found a decision how you want to calibrate, you have done your job, you can select and write into your maps and curves the right values. So how is now this calibration workflow supported by Cameo? So there are more or less two parts of Cameo. We have the Cameo online part, so driving a test, where you have here a main workflow consisting out of the project administration, of prepare test, run the test, and in the end you will get results. And for each of these steps, plugins, you have here a sub-workflow. So you can organize first your projects in a database. And typically you connect with Cameo to one or several systems, like an engine test bed, like an application system via ASAP3 interface. So Inca, you can change via Inca, or a application system might be Helios or from another company. You are able to change parameters in your control unit while the engine is running. And if you have your test result, in a classic way, you go to an evaluation. So you build empirical models to understand the system under test and to use it for optimization. And this again you use to populate maps. And again, there you have then a sub workflow. So you start with the test results in the raw data, have a first check, and go then to build the behavior models, to watch also the behavior models. And if you have this, you can then go for optimization, and a bit below you would find the map calculation. Well, now a small example how to reduce the measurement numbers. So here is the workflow, and I'll talk first about just the task definition, the design, and how to run a test. In a second step, and I will do this live as I have no testbed connected here, but I can show you live the offline part. This will come later. So first, you have also to know, coming from the DOE side again, you have to make up your mind for a start design for motor tasks. So in case you have pre-knowledge regarding the non-linearity of your responses, maybe even for different directions, you can say, this has small influence, the temperature is just a slight influence. Cooling water temperature maybe will not be the hell of influence of to the emissions, but a bit maybe. You can say in this direction, linear or second order only. But the ignition or the injection timing the degrees of between the injections. If you have a diesel engine, you have 2 or 3. There is a pressure wave compensation function in the ECU, and whether it's working or not, anyway, you have a strong influence of that in the injected quantity and thus in the operating point. So the NOx and fuel consumption is strongly affected. So maybe you can say this angle between pilot injection and main injection, or the 2 angles, if you have 2 pilot injections, there you say this is a 6-order influence. And still you can work with polynomial models, separating high order or low order. And if you can do that, typically we say it's reasonable as long as you are in one operating point and not going to a global model above several operating points. And if you have not too strong constraining borderline maps, again, if you're in an operating point, yes. If you're going to global model, no. Because a rail pressure map is, yeah, you can change plus minus 100 bar maybe, but it's going from 800 to 2000. It's strongly load and speed dependent. So if you can say this is not the case as you are in one operating point, then take a de-optimal design. A start design is the most effective and working very good, very well. If you have to say to the same questions, oh, sorry, I have no idea about the nonlinearity. Smoke will go up somewhere, I don't know where. Narrow borderline maps for global modeling, I want to know it all over the engine map because I want to do RDE calibration. I need to be able to shift the operating point anywhere, not only in special measured weighted operating points. If you have this request, then please take a so-called S-optimal design. So this is one of the so-called space filling designs where there is no input needed regarding the model quality, the model which later will be built. And at the end, this technique, it gives you a lower number of points with still good coverage of the borderline and also inside. There are again several techniques possible, but these are the 2 recommendations we give up front. So for example, also an E-drive, if you have this angle between ID and IQ, gives you a small area where it makes sense to operate this e-motor. And in this range, typically you can maybe win some noise benefits. Okay. How does now our test bed look like? If we look for combustion engine, there's typically the system under test and engine, consisting also of a control unit, connected to a dyno simulating the environment, and typically 2 parameters physically for the power of the engine. One is controlled on the engine side, it's maybe the torque, and another one is controlled on the dyno side, it's maybe the speed, and it's the control unit MCON is the part of an Puma test bed, if we talk in AVL test bed language. Then you can measure or should measure most of the cases the fuel consumption. You want to observe the combustion with a cylinder pressure measurement or other fast measurements, indicating in the master is a good choice. You want to observe the emission bench, so we have several products in AVL to do so, also for the smoke meter and opacimeter for the smoke. Also, there are other options. But anyway, you have measurement devices connected to an automation system. And then there are standardized interface, for example, to an application system like Inca is the market leader. But as mentioned, there are others out there, ATI Vision in America, for example. All of that systems, luckily, support the standard ASAP3. Well, not luckily, we forced this 25 years ago to have such a standard. And yes, it's very good to have standards. Well, up to now, you don't see any CAMEO, right? So what I'm talking about CAMEO now, this is an engine test bed. Yes, you could make, for example, a manual operation or a few sweeps with some few variation parameters. But if you want to apply DOE, you should connect Cameo to such a test system. And again, we make use of standards. We take for sure the ASAP 3 standard to get access to the application system. And also to our own test bed, we take a standard. Well, we have internally even a slightly better interface, but in principle, it's possible to connect to all test beds supporting this ACI standard, automatic calibration system interface. Although this standard has now, I don't know, 18 years age. Okay, and out of Cameo view, we talk now about systems. So for example, we can make here a line around, and this would be uploaded at the beginning of the process towards Cameo, a so-called ASAP 3 system. What's happening in an upload? Cameo just asks, please tell me the parameters which I'm allowed to set to you to change the maps, which maps I can change, how they are named. And please tell me also what you can deliver back, what you can measure. Yes, and the injected quantity, for example, or other models maybe, or sensors which are taken here. And therefore, it also makes sense to have it connected to the automation system, and from the automation system, we pass it over to Cameo. And the same we do with the testbed system. Also there, we get all the norm names available in the Puma system, all the control modes, what it can do with the system under test, and load it to Cameo. And the test parameterization is then just selecting these parameters and doing a comparable fast parameterization, not programming work, of a test run. Here we have more or less the same for an eDrive test bed. The system under test is an e-motor with an inverter. We need somehow a power supply, which typically is a battery emulator, where you can request a certain DC voltage, and it's reproducible. If you would have a battery not so reproducible, it's more challenge. Then to measure the power going towards the inverter and the 3 phases power going to e-motor, again, you need fast measurement technique. So it's Xion. So it's at the end, nothing else like indication, but always a bit eDrive features to get the power. And also the dyno, the mechanical power to measure, is not so trivial anymore, because we have somehow torque oscillations, and such a working cycle of an e-motor is comparable fast. And if you want on such an e-motor cycle-based a comparison with the torque, you need to measure the torque in the same system in megahertz level. So this is delivered by the Xion. And the result on, let's say, kilohertz level is then delivered to Puma. Puma is also considering and measuring all the other automation quantities. Also from Inca can be routed via Puma, can be connected directly. With Inca, we talk then to the inverter ECU. So we have again 2 systems, the testbed system and the ECU system, or XCU system via ASAP 3. And just as an example of what it happens in eDrive tasks, some models need to be calculated maybe in MATLAB, and you can also in parallel connect a MATLAB system. So on all the 3 systems, you can select or change DOE parameters in a Cameo test, then request to do something. Typically, you request this from automation system, and get back measurement results from all the systems, and make behavior models of that results as function of the parameters you have set. And while doing so, you have also some limit observations and reactions. Therefore, a so-called test procedure is necessary. And I start here with a very simple one. So it's also for DOE. typically this two-layer structure is the one which is needed. So if we start in the workflow, we have here the prepare test. We work with certain systems and we typically use two layers. For example, in a full factorial mode, on the first layer, we change the operating condition like speed and torque. And if one speed is reached, it's going to the second layer. And in the second layer, we change the parameters which we want to change inside an operating point. So this is the classical approach proven since more than 20 years. And this principle is still the same also for advanced active global DOE test procedures. Therefore, I just present that one. You might have subtests as reaction of limits, a cool down point, for example. And now let's have a look what is happening during test run. So this would be maybe the first layer, and we have done the points up to here. And if it comes to that point, in each of the layer happens the same. First, an operating condition is set, then stabilized, and if you want, you can make a first measurement there. Typically in between, you have trigger points, which are named intuitive before stabilization, after start, before measurement, after measurements. And at that point here, which is marked, it automatically goes to the second layer. And here does again the same. It sets a point, stabilize it. So you start here with a starting condition. Then you take a measurement and you look this through whatever is in this list or also in the procedure in this second layer. Here's a very simple list. It's a sweep towards the knocking border. Sorry, it's not a gasoline engine. It's an e-drive, but there you have a similar thing. You have a voltage limit of the voltage ellipse. So it's quite close at the end. Fast process, like knocking. And you have to detect it with a device like Indicon. Well, you measure as long as you come to such a borderline, which is then a limit. And here you can specify several reactions. One is step back and reapproach, but in this case, you have done everything. You're ready, and you are going then to that point, to the first layer, and just set the next point. This is the simple automation. Always this structure. For parameterization, you just need to say what should happen in the first layer and in the second. And you have also wizards to populate your ranges. If it you have several variations, what is typical if you have a DOE. Then there is, in this second layer, a special so-called screening and adaptive mode. I would call it careful approach towards the measurements which are planned. So for example, here you see there's a measurement which is not yet reached. It's gray. This one is already done. There is also one which was intended to reach. And you see there are small dots. And typically, for example, this beam from the starting point, it's approaching that point. Well, there are more than 3 parameters. Only 3 parameters are displayed here. So in the first one, he could not reach that one and made a step back here. With another setting on the same beam in this picture, he could not even reach that one. He had an issue here and stepped back and measured here. So it's comparable fast if their limit is going back to that point where it was still okay, coming from a safe point. So this is how the DOE is applied on a system with hardware, which could be destroyed by the setting. So there are many options to destroy, for example, combustion engine just with calibration. If you have a gasoline engine and apply 2 early spark at once, you will get knocking, which is typically not standard for more than a minute if it's heavy knocking. If you have a diesel engine and to apply too high peak pressure, and you would like to run an automatic test run overnight, and you would do this without limit monitoring, you might not find the cylinder head in the position like you left it in the evening when you approach in the morning. So it's important. You can easily destroy a hardware with calibration parameters. And this was the first issue to solve it all, to get DOE towards a test bed. Yes, and this is a bit more shown here. What you can do, DOE is at the end a list for several variation parameters, any numbers. So at the end, you set this number to a test bed. And if it doesn't work because a limit is violated, what you should do? You just can go to the last one which worked and try the next. And if you apply this in such a brute force list, I would say, and this list are far distant points, you might jump very far into the forbidden area and risk really to destroy your unit under test. So a DOE list is only recommended if you don't have serious limits. If you have limits, you should do what we have seen before, approach in small steps. If there is a limit, at least step back. Or for knocking, it has proven to go far back, step back and reapproach. So to go then one step less. Anyway, when you do so, you will shrink your design space. And this might work for later modeling or not. So out of that knowledge, we applied already 2005 or something like that, the adaptive online DOE. So it starts in the first step exactly like this DOE screening. But if you have reached this range where you might have shifted a lot of points here together on that side and here are many empty spaces, it starts again the DOE designer and fills in the space which you know now additional points to ensure that the requirements you had for your design will be fulfilled. Still full automatic in the same test run overnight, and in the morning you find data which you can use for evaluation. And now what is this latest development, this active DOE? The working title was Custom Output Range DOE, Core DOE. I like this a bit, despite I can only use in a lecture like now, where you have the chance to talk a bit, because it covers quite good what it is doing. For example, smoke. We know smoke is difficult to model. We have, for example, if this is EGR rate or swirl, or I don't know what it is. Anyway, with a high rate of this, the smoke is going up, EGR, let's say. And if you would make a polygon, if you have even 4 in a row and one beam, it's a lot. Typically, don't have that. But if you have 4, you still have, if you make a polygon, one option. If you make a very sharp neural network, you get another one. If you make it a bit more soft, you get another one. Which is now the right interpretation of this measurement in this range? If we don't have more measurements, we don't have a clue. So if you say now, I'm interested in ranges between 0.5 and 1.5 FSN for smoke, I'm not interested in values above because I can't use this anyway. My particle filter will get blocked too fast. I can use this knowledge because the application engineer knows it up front when he parameterized the test, and I can just request him, where are you interested? And in the measurement tab, he says, I'm interested in the range between 0.5 and 1.5. Well, after first modeling, then he goes here to the borderline and says, okay, let's have a look. What is the value here? And then the measurement comes back with this information. And just within one measurement, you get more or less a safe modeling, which is reasonable. And this works for sure, not in one dimension, but in all 7, 8, whatever is needed. And yeah, it is again now out of this eDrive validation tasks where we should validate the temperature in the high temperature range, where nearly no measurements were there. At the end, it must not exceed 150. So we said it should target this range above 120 up to 160, and got therefore some points here and got a reliable model of the, let's say, error at least of these two temperatures of the diode and the IGBT, which is a semi-physical model implemented in the inverter and needed to be validated on the test bed. So the same technique can also be used for validating a model without recalibration. One could recalibrate also, but also validation needs sometimes already design of experiments. Well, and now I come already to a kind of summary of all what we've heard in terms of test procedure and DOE. So this, let's say, lecture part will close at that point. So the difference of a test procedure and the design is more or less something you can calculate with statistics and mathematics. Test procedure is what you do with this list. So in simplest way, you can just apply the list step by step. It's fast, but limits you lose, and you might jump in very fast into the limit, far into the limit areas. So if you have limits, better don't use it. At least if it's dangerous for the system on the test, don't use it. There you should use an online DOE screening, or even we don't differ between those two. An adaptive DOE, which is doing exactly the same in the first step. It keeps the number of points defined and shift it towards the drivable range inside. And the disadvantage is the design you nicely made before is distorted. And in the second phase, which might use out of this side, which will come, a D-optimal or S-optimal design. This design is then recalculated and, let's say, repaired, adapted to the drivable range. And so you're green again. Beyond that, in the active DOE, again, the same steps happens, but the model is also built automatically. Not only the design is checked, all the models which might be used for optimization, and even the optimization is done online automatically if you request it. And you can put, for example, the area of the populate the area of the Pareto front, or you say, I'm interested in a certain range of unlimited number of outputs, and you can define this custom output range. And you can start with a quite simple start design. The active DOE will adapt automatically to the area of interest and make their high quality model, and the rest maybe is a simple model, but you're not interested anyway in this area. So this increases quality and saves additional points. All what I've said now is only about test procedures. When we talk about DOE, maybe you've heard it, I sometimes mentioned it, we separate between polynomial models, which is, let's say, the elder technique, which still makes sense for simple tasks where you have not so high nonlinearity, and polynomial nonlinearity might go up to 6 orders, is quite nonlinear, but polynomials are tending to oscillate if it's going to higher nonlinearity, and yeah, is limited in this respect. If you have such a thing in mind, nevertheless, local operating points to investigate. There are several designs which we support with a clear recommendation towards the optimal, which is the most modern and most flexible design. Can be adapted exactly to the task you have, if you have pre-knowledge. If you have no clue about the model and want to be able to fit any model, there are several space filling models on the market. The very famous is the Latin hypercube, which looks very nice in graphs, is not that good as it looks. Anyway, we recommend this S-optimal design, which you can compare with let's say if you have somewhere a design space, might be shaped strangely, and you put in this design space magnets without gravity, but with forces against each other. So this design has the trend to maximize the minimum distance. So it's first filling the border and then going inside to have an equal distance to each other. And this in any shape. So it's a quite powerful design. Needs some calculation time to calculate first time, but it's negligible anyway. This is a few seconds or minutes in worst case. Good, this is the summary for the online part, and hopefully I still have, sorry, I have to apologize. I want to go live with you a bit through the evaluation, how to get to such models, make a decision, design decision. And now I will put maybe just the question shortly. Is it okay if I still go through this part, or are you already tired because I nearly talked an hour already?
I think it's very interesting, and as for me, if you can keep going, we would be happy.
Okay, then thank you very much. Then I go ahead. Thank you for the feedback. It's always nice to hear that I'm not only talking to a PC, but that there are humans behind. This is always a bit difficult in these times, but a bit one gets accommodated to that. Well, if you open Cameo and you start, you get here is even, by the way, the default demo database, which is delivered with Cameo. You get here a project administration first, and you see here the main workflow, which consists of a few on the projects you have in your demo database, and the systems which you might connect to Cameo. So they are named according to the interface. You can have a .NET interface, an AVL real-time environment, which is testbed connect mainly, ASM ACI, ASAP 3, I just named now the more important one. This is to the Inca. This is to a standardized other testbed, foreign testbed. Puma ACP is to Puma 2 onwards, which have some more power than the standards. What else? Simulation desktop, not unimportant. All our tools in the, let's say, physical simulation, like Cruise M, the basis Model Connect with FMUs, you can put together their FireM, Boost, Excite. All these softwares can be run and reached via AVL Simulation Desktop. We have also a simulation interface to CarMaker from IPG. For data evaluation, and also reporting, we can connect to AVL Concerto, or we can ask Drive to get ratings of drivability. If you miss something like an operating point and you need it, you have a dummy system or test. There's more to test Cameo. iLink real-time, a very powerful, fast connection to ECU. If the ECU supports this iLink interface, what some of them does. You can get results from Indicom directly. You can run some MATLAB environments in parallel. You can run Simulink, which is where it's delivered a compiler with Cameo in the so-called non-real-time environments on a Windows basis. For this R, that's real. You need a real-time environment, AVL real-time environment. This is just Windows. Yeah, Python maybe is also important. It's modern, and if students are listening, all of them learn Python today, and you can do a lot with Python. Yeah, we are quite open with that, with the system. Well,
sir, just a minute question.
Please.
For ECU specifically, what protocol will we be using?
ASAP 3.
Okay.
Typically the ASAP 3 system. And the good thing, if you make a new system, it's always looking the same in Cameo. You give a name. It's ASAP 3 is not very, this is just the interface. You could name, this is the ECU MED. I don't know what is the actual one. 7 is over a long time, I'm sure. Then you might give a description. You say some connection properties, mainly important. Where is your ASAP 2 file, A12 file? You have to enter. You can browse where it is on your hard disk. Also, there is a log file which is placed in a default space in program data, and so on. Some connection properties which have to be set up. You get it with commissioning. If you have a testbed application, you should apply and ask for support in commissioning, that everything works proper in an acceptance test. I think you will get even a real-time controller to set this up once. It makes absolutely sense to have an expert on site who knows all the systems. If you have set these connection properties, what I didn't do now, to be honest, I don't know a path to an A12 file. I'm not prepared to that yet. But if you would have, you could connect, and then in the first step, it would try to find now with these system properties the system where nothing is here. Then you could import the system. He would read. Yeah, he doesn't find any A12 file. And you get then here a selection of the channels. So you get maybe offered in the A12 50,000 points. You can select the ones you are interested by a search function and store this in a lab file, or you can get such a lab file also from AVL Creator, what is maybe on the university, not the tool you will have. But in the industry, yes, it's already a standard to manage calibration data, because there are so many variants that you, for certain tasks, have defined subsets you want to work on. Yes, and this you import, then you have here some devices for Inca. You can start and stop a recorder, for example. For a Puma, you get control modes. You can have speed, torque control, or speed and X control for quantity on the engine, and so on. Yes, and this is what you can do. That the menu is always the same, regardless whichever interface. Sorry, I'm now in the system. If I look at system in the system, doesn't work, I have to go outside. If you take maybe, or I have here, for example, a CAMEO system, you see then here again some connection properties. You see here channels which you might read or set writable. These are maneuvers in a vehicle, so it's ego velocity, cut-in distance, other validation task is what you have here. And you see also some readable, where you get maybe some KPIs, some maximum braking deceleration, minimum distance reached to the obstacle, such things. KPIs are responses in this case. Yes, this is, so maybe even too much, answering your question. So ASAP 3 is your choice for ECU.
Thank you, sir.
Gerne. It's so nice if you, I can't Czechish, sorry. I have to stick to English. Anyway, if you then set up a test, you get here automatically the plugins you need for a test. And here on this side, the same again. You give a name to this test, what it's done. So it's, in this case, a comparable old example for a Euro 5 calibration of a heavy-duty test cycle. Here is this written that you had 6 variation parameters. You made it in modal, 13-point test, 13-mode test, and local models with 6 parameters using a de-optimal test. Adaptive online DOE was used. So a bit of summary of what you did. You can write here. You could have even several versions of a test, which typically comes later. You might do later a verification test. you get a copy of the same test, but can overwrite a bit, and you have your verification test. Anyway, you can copy a test with just copy-paste and structure a database. You can also make templates, test templates for new users. So much, I must not say too much now, else it gets too long. And you select your systems you're working. In this case, we have an NRT sim, heavy-duty simulator, so I can run even this test. But I will not do it now because test I explained already. If we have time at the end, I can do it. And you would see how a test typically runs. And then you can go to the next steps where you prepare the test, where you prepare the 2 layers, and you get a graphic representation, in this case of the operating points. And all the other things are options which are even not needed in this case. So I prefer, I said this several times, that in the default it should be done like that. You need not see that because nothing is in. So at the first layer, you just have typically the operating points. You select the control mode and the speed values. You get a wizard to fill it. You can type it in. You can import it. You can use a global DOE. Yes. And on the second layer, for each of the operating points, so if you want to get all together, you can mark all together and look in the second layer. Now you get the variations, and you can see in this case, there were mentioned 6. You have 6 variation parameters for each of the operating points. You specify the area from 2 and also where it should start. And you can fill then in this range a list where you are supported again by a wizard, a local DOE, or you could import a DOE. I have to stop as there are too many details. You can apply actions, special parameters, some details which designed for adaptation, for examples. Limits, very important. You can say, please, while your measure don't exceed 180 bar, turbine inlet temperature below 800, turbine speed below 120,000. If this is reached somewhere, Cameo will take back to save the hardware. You could apply a response controller. So you could say, I want to reach, for example, a NOx not higher than, and you have as control parameter the start of injection of the main injection, and you just retard to get to make a kind of simple online optimization. You can have stabilization times. It's not always the same time needed to get a certain temperature reached, and you can specify tolerances or gradient tolerances to shrink the stabilization time or to extend the stabilization time until this is reached. And in the variation, you specify a stop time. You see it's quite short stop time because stabilization criterion is used here, and the short time is elongated until these conditions which are defined here are reached. And last but not least, you specify the measurements, what you want to get as response. If this wouldn't be an adaptive online, but an active DOE, you would get here the columns to enter the range where you're interested in. More or less, that's it, what you have to specify. It's like newspaper reading. You start here on the first layer, second layer. If you're on the end, you're done. You can go to the next step and could run and start the test. Just to save some time for the evaluation, I jump out of that and go now to a very simple evaluation, which is done here for an injector comparison only in one operating point. And by the way, this structure of examples we are in the process to fill, there are just a few first ones which are here equipped with an PDF where the task is explained and some hints are giving what you see. So the injector example is, for example, ready already, some fuel examples others examples. Fuel cell are in, and for sure some gasoline and ICE examples. Well, and if you have such an evaluation, you can look now first to the raw data. Start here with the first sub-workflow. So you can import data from somewhere, from a file, from a Santorin Asmodee database, or any Asmodee AVL product is Santorin. You can for sure take any test of the CAMEO database or also another evaluation. And you can select whether you want to use it for modeling or as verification data only. You have data already in. And the data are displayed then in a kind of Excel format, table format, let's say. And the main thing what you can do here, you can say it's a variation, or it's a response, or you keep it as measurement, where we don't have any here. Yeah, anyway, what you have here, you can select what it is. Some channels you could calculate. You could also, for more complex calculations, export to Excel and take it back in again. You get a first graphical view where you can select here out of standardized graphs, which are useful and fast to see. Some for the raw data analysis, so the variations over time, measurements over time, variation versus variation, and those are the three first one I would check, and I've prepared here. So you see, for these 4 dimensions, we have made only 40 measurements. It is a de-optimal design. It's a polynomial behavior. It's only inside one operating point. We changed rail pressure, MFP50, so start of injection, but we used MFP50 to model as input parameter. So you know what is mass fraction burned 50%? It's the angle where 50% of the mass fraction is burned. Also, lambda was varied and the EGR rate. And in this range, only 40 for 4 dimensions. So if you would take, let's say, 10 just to calculate fast, it would be 10 with the power of 4, it's 10,000 full factorial grids. In this case, only 40. So 10,000 you never would do for that, but 40 is comparable low. And if you have this view, variation versus variation, you see a 2D projection from all possible sides. So if you would have 3 dimensions, those 3 would be top view, front view, side view. And if you have 4 dimensions, you get 3 additional views possible. And what you see here is just how good the space is somehow filled. So it's for the 40 points quite nicely filled. And if you then go to measurements, in the raw data, you can just judge whether you have strong outliers or not, or maybe zeros or infinite. If the smoke meter doesn't respond, Puma delivers 10 with the power 9. You clearly see this. You have also additional options for outlier detection. And you have here a repetition point statistic. You see how the standard deviation of the repetition point. So how good you can reproduce the several events. Okay, if it looks like that, nicely covered space, no big outliers, at least for the 3 things we might be interested. We are interested in more peak pressure also and so on, but I don't go through all. Next step is then modeling. And again, here you get automatically a suggestion a bit, as we are in university, I start on that side. You could define the model type. Per default, it is set to automatic, and you just say build model, and then in the background, the CAMEO tries out of the several options to make a good model here. And then you get some quality indicators, which are now too much to explain what it is, based on statistics. And yeah, here the models seem to be not good. This is this is still okay. it is a controlled parameter. It is the charge air temperature after a cooler. So it is controlled to 50 degrees, and it couldn't be controlled completely. It's between 49 and 51, but is not related strongly to the variation parameters as it should be at the end. So you get here now models, you get here a picture. Also, for example, for the peak pressure, it's the model predicted value. You went even up to more than 200, but 200 is a borderline for that engine. And here you get the measured one. So if this is on a 45-degree line, it's good. It's not completely reached, but okay. Smoke is the typically most difficult one. It's excellent. Yeah, good, this gasoline engine. But still, yeah, considerable smoke. Yes. And then maybe the most important are the graphics. If you start with a 3D graphic, this is what we are used to see. You have here two parameters, maybe rail pressure and MFP50, start of injection. You see a strong influence on fuel consumption, also on NOx, which is typically the contrary direction. Again, different is the smoke. And we have now two additional parameters you can't see yet. You could see, but then the pictures are changing all. And if you change now EGR rate, you see fuel consumption is swiping a bit, smoke and NOx are doing different things. Yeah, as to be expected. You decide somehow if you change lambda, all three are changing. So you see that 4 dimensions are not so many, but are already a challenge for our brain, which is made for 3 dimensions. So at the end, we make here a 2-dimensional cut out of the 4-dimensional input and watch each of the diagrams with one response on the 3rd dimension. So now the idea of the intersection plot is, I would say, quite interesting one. I just go back to one channel only, so the fuel consumption, brake-specific fuel consumption in grams per kilowatt an hour. And so if you change the EGR rate, in this case, it's even nice, it's going down. But this behavior changes and depends a bit on the lambda, what you're running. So you see here already an interaction. For sure, the more you will retard, the more energy you get in the exhaust and the less efficient is your engine. You can compensate a bit with higher rail pressure. You can win something. Yeah, if you would now go for the lowest possible fuel consumption, you could do it even by hand. And yeah, you could give even some EGR. Yeah, you come easily below 220. Now let's have a look what smoke is doing. Yeah, it's on 3. So you should do something about that. Yeah, you can reduce EGRs at least, and so on. You can sweep through that, and if you now see also the NOx at the same time, you really can learn combustion. You can teach it with that. And yeah, it's interesting, I would say. You start to understand your system at the test. You could also give maybe a void to see now the optimum in 3rd glance, to have one cursor. And yeah, you can sweep through here, make up your mind where you want to go. Maybe you don't want to exceed the fuel consumption too much. Nevertheless, you would like to go down below 1, maybe with the NOx. But below 220, it should be. You don't find this easily here. Well, we have now models we can ask an optimizer. And as we don't have so much time, I directly go to that example. You can start with definition. Here you define the target functions, function or functions. If you are not clear, we want to, at the end, we want to minimize all 3, fuel consumption, NOx, and smoke. One option is to make a trade-off between NOx and soot or smoke. We have smoke values here. And make a constraint on the fuel consumption. And here I applied 220. And for sure, constraints on the hardware parameters, so peak pressure, in turbine inlet temperature, turbine speed, and so on. These are constraints you have to consider anyway too. And if you now ask to optimize that, the optimizer is not delivering one clear result because you asked for 2 targets. And so you have to decide at the end as calibration engineer what is more important for you, to have a low NOx or to have a low soot. So if you go for the best possible NOx with this fuel consumption, you can easily go, no, not easily, you can go below 1 grams per kilowatt hour. Maybe you say 2 is also okay because you have a DNOx cut, but you don't want to have too high smoke rates to have too frequent regeneration for your particle filter. So you could make up your mind and say, I want to go in this point, and yeah, or you could investigate first any other point on the Pareto front, and you will see automatically here on the intersection plot in which area you are, with also the design space, which is this green bar in the bottom as constraint. So he must not go outside of that. So if you allow him to go outside there, yeah, you might find some better things. But in this case, we move away from the Pareto front. It's not so easy to beat that suggestion. And so we can go back to the optimum and say, for that injector, we would select these points. We are below 1 smoke and in the range of 2 gram NOx. This we store as result. And at the end, we got 1 result, which is stored there. Wow, it's already 54 minutes. So I would like to, we can then compare also 2 variants and have a graphic there and compare 2 hardwares, for example, and see, yes, the blue one is maybe the better one compared to the black one in injector 2, which delivers a bit more smoke. And we can also see how the 2 intersection plots are behaving when moving away here. Anyway, I'll come to the summary and leave you at least, I'm available longer also, sometimes for the questions. So if I go back now to the presentation, we had ended up with this picture, and we could say we select, in this case, injector 1 with this calibration for EGR lambda MFP50, so the corresponding start of injection behind rail pressure. And we have done our job of injector selection and calibration, at least for this one operating point. What is now the summary? The crucial breakthrough to apply DOE in an environment like an engine testbed is the automated model-based calibration. This has several elements, and these elements are the methods itself, the test automation, the access of the ECU, then also map calculator calibration tools, the online modeling and the intelligent adaptation automation. So first, towards limits, not to exceed. Second, also active QA to get the high model quality in the area of interest. With this, I would stop my presentation, and I'm happy for any questions which might come.
Thank you for this interesting presentation. I am glad that the COVID situation not only take away from us, but also gave us this opportunity to have you here without traveling. So
yes, we will. This option we will keep further. So yes.
And also I would like to let the students know that we were granted with 10 licenses within the university partnership program with AVL.
Yes.
So we do have available Cameo here. So if anyone is interested to try and test and play with it, so please, you can contact me and we can provide you the access. We still have 28 listeners, which is great. So now here's the floor for the questions. Professor Macek, please.
Jan, nice to hear you. Maybe no tone.
Microphone, please.
I have also to find the window again. There must be somewhere.
Honzo, neslyšíme tě, máš vyplej mikrofon, prosím.
Sorry for it. I am glad that you are here, Hans Michal.
Yes, thank you.
Virtually, and I am glad that the result is this one. I will not comment the details. It took some time, but just now it is okay. My question is, you have spoken about possibilities to use Cameo for testbed. There are, of course, possibilities to use it for simulation, just to evaluate simulation results as well. And is there any possibility to prepare the real experiments starting with simulations, just to say, to have a rough idea about the limits of engine and so on, and to use directly the simulation results as the first step for design of experiments in Cameo?
For sure, for sure. So maybe this overview is showing a bit. You can connect the simulation environment, and we have done a lot in simulation, especially if it comes to component selection, to designing parameters, but also with the virtual testbed, the VTB. So it's even shown here with a very small picture. So there's just the ECU and the virtual model, which is called Mobeo from AVL, running on Cruise M. And you can access this like a real test bed. And also what we have seen here in Cameo Live, I can go back, maybe we had it there, I think, yes, in this example. We have here a diesel simulator. Well, you can use it for your training courses. Mm-hmm. If you want to set up, for example, a DOE training, or if you want to make a pre-investigation, we did nothing else here than exporting models gained from a test bed, maybe also from a similar engine. And here in this environment, we can prepare a test, and it's even running in the background always. I didn't stop it. You see here now, I jumped this point. The low load was a bit boring. Now we're again in a low load point. Sorry for that. But here he even had a start limit violation. And you see here now how the approaching works. This is reasonable times. It's now 10 second stabilization time, watching whether a limit occurs or not. It's like on a test bed. Yes, and I could maybe just jump away to that point, maybe a bit too higher load. So you should see now, now there is changing. I have to look what is orange torque and the speed. So it's now going up to that point. He's here in it, setting the point and ramping up to that torque. Yes, so a clear yes, Jan, you can do that. You can do it upfront. Check areas of a similar device, train people. This is more or less for showing how it's working.
Thank you. And the second question from my side, you have spoken about polynomial models and then the models which are more or less, say, trained models using neural networks and so on. Is there any possibility to use some models which are polynomial, which are not only polynomial, but which are more based on physics? For instance, for efficiency curves, it is a very good approach just to describe the losses in engine in a polynomial model, and then to use, in fact, more complicated function for efficiency, which is something like brake power divided by brake power plus losses, and losses are modeled as polynomial model. Is it something like it possible, or how to do it?
It's possible, and how to do it?
No, not. It is not.
It's maybe too short now.
It's a procedure, but yeah.
Yeah, I can show you one thing very fast. You have seen now here these injector models, and for each of the models, what you have, you can export it, and if you can create an online system now directly, you need not extra compile it, but what is also interesting, you can export it in the following ways. You can make it to Excel, to Simulink, to MATLAB, to a functional mockup unit, to Python. And then you can calculate in one of those systems whatever you want, and you can connect it as system again to Cameo. So this is the way how it's possible right now. And yeah, this is already quite comfortable. Whether we make it even more comfortable in future, I don't want to exclude it, but it's definitely possible.
Thank you very much.
Maybe some other questions?
Maybe I will have a question.
Yeah.
Is it possible to connect Cameo with GT Suite or GT Power?
GT Power, yeah, we had such applications already. Sorry, I'm not sure about the camera. I don't see the window. Should I make some light maybe? Else I will get too dark maybe. GT Power, well, let's have a look what we could use here directly. If you can start a GT Power via Python, this would be a possibility. Or in the simulation desktop, when you connect it somehow with Model Connect, might be a possibility. I don't remember how they did it. Well, I remember that the GT Power is more or less a similar thing than our boost, right?
Right.
And yeah, there are options. I can't answer you directly now which one is the best, to be honest. But okay. There are.
But the good news is that it's possible.
It's possible. Also for the test bed, we never, despite we had some conflicts in AVL, we never said we only want to connect to Puma only. We're open. We're open to, and this is the right path because our customers have a problem and they will not throw away their test bed just to apply Cameo. And it's vice versa. I remember in Korea, we've got an order for a Cameo test bed, what is a kind of wrong expression because Cameo is not a test bed. They meant a Puma. First they bought a Cameo and then they want to have from AVL the test bed in addition. So maybe if you see the options, yeah. But GT Power is also a good tool, I think.
Thank you. Any more questions, please? I don't see any hands.
Okay.
So I'm very glad that today I learned what does the CAMEO stand for. That it's computer-aided method for every optimization.
Exactly.
So it was really nice to have you here. So I would like to thank you for this nice, very interesting talk, and hopefully we will see you soon in some, let's say, better conditions than
Who knows? Who knows?
Situation.
So. So I also want to thank you for your interest and for the option to talk to you, and maybe want to engage or encourage some of the students. If you have an idea for your master thesis, also there might be a good option to investigate some things using Cameo, and with your university, they have now available the software. It's an option to get into this tool and to learn it. And yeah, this is one of the good things what we are enable with the university partnership, to get persons who have done already some jobs with Cameo, have learned the benefits, and thus when you go out in the industry, you can give a hint to your employer that this might be an option for him too. So,
sir, just one last question. Like, do you have any case study evaluation documents available for the public so that we can use it for study, like documentation?
for sure.
Apart from what you have in here inside the software?
Papers, you want to have some, we have a lot of papers, but also a good online help first. So if you press F1, you get a quite good help. Yeah, it's a context help, so you have to be somewhere else you don't get anything. But if you maybe go here, modeling, and yeah, press now F1. I have to press function F1. That's the point. You are directly in, you get an explanation, you get also application guides delivered with the software, and now these demo examples where each of them has a short explanation. And for sure, if interested in a scientific way, there are a bunch of papers to many topics outside. And yeah, it's used by the industry, it's used by universities. It's also a chance for the university to really get fast forward into topics where you are not reinventing the wheel by making your own modeling, for example. You can do it as an extended for sure, but you get for many topics already a big advantage if you just use this tool set what is available already. Not sure if I answered your question. You asked for documentation or what?
Like, if we see inside here, we have I think 2 case studies available for gasoline engines.
Are you still here? I don't hear you now.
Am I audible now, sir? Am I audible?
Is anybody still there, or is the meeting ended?
No, there is still 25 listeners in this meeting.
Sorry, I muted my loudspeaker, so if
okay.
You said something, I didn't hear anything, so I was confused. Sorry.
So here we have inside case studies available. Do you have any what do you call documentation separately on how to do it for this for gasoline engine calibration?
Yeah, the whole gasoline engine calibration is a wide topic. We have, for example, the gasoline is even there somehow an example where you have, I think this example is done already. No, it's not done. Not done in a way that we have here the PowerPoint. Maybe, no, not yet. gas line calibration is more or less air determination, torque mapping, knock detection. These are the three elements of the base calibration. And then also in the base calibration, if you have valve timing, then this topic of variable valve timing calibration is somehow in. Yes, the calibration engineer background directly is not fully delivered by Cameo, but if you have a task, some of the tasks are explained here, and I have to look in the documentation where I should know where it's stored. It's somehow in users program public. There is a documentation delivered. I might be not able to answer right now to show it. I hope so. I'm too far away from the application support now to directly. Maybe you can look with me. Users. Maybe it's directly in the own one, or it's outside program data. There's program data. AVL CAMEO. This is a bad point now for me. Sorry for that. I should know it. There are some user rights for Windows where you can write in and so on. And there's a guideline. Maybe the young guys can help me. But should be on the program data. Well, there is a certain application guideline on one example, very detailed, where you can learn Cameo more or less. I might be not in the position to show it to you right now.
It's okay, sir. Thank you.
You're welcome. Sorry. So, some further questions, which I hopefully might answer. If not, I would have a question: how to get back the Teams window to see you? I don't find it. Maybe if I stop sharing, then it comes back. Well, if there are no further questions, I would say thank you for the chance to get a bit in touch. And yeah, I wish you much luck and success with your university partnership and applications. And please let us know if we can be of assistance. And yeah, with this, I would wish you a nice evening then.
Thank you very much.
Thank you. Goodbye.
Bye.
Thank you. Goodbye.
Thank you. Goodbye.
Thank you, sir.
Gerne.
Okay. Bye-bye.
Thank you.
Bye.
Bye-bye.
Tja, is still someone there?